I have the pleasure to introduce you, Lars Ruthotto. Oh, yeah, I'm sorry for spelling your surname.
It's okay.
Who will give us the continuation of this morning's view on looking at continuous models for neural networks, I guess. It will be the PDE framework now. So I think the floor is yours, Lars, please.
Cool. Thanks so much, and thanks to the organizers for inviting me. And thanks everybody for coming back after this good lunch. So I will talk today about PDE-based algorithms for convolution neural networks. So that's basically taking what Eldad has introduced before lunch to the next stage to make one or two or three more dimensions here continuous in this deep learning problem. This is a joint work between Emory, a small startup Extract, and the University of British Columbia. Those are actually the people who deserve all the credit. And of course, I'm also grateful for some funding, also for a nice GPU that I got from NVIDIA to actually carry out all these computations. Okay, so that is the rough outline for today's talk. I'll briefly review deep learning as a dynamic inverse problem, just to bring everybody back into the spirit, but then I will move on and solely focus on CNNs. So that's convolution neural networks. And first of all, I will establish an interpretation of CNNs as PDEs. Second, I will talk about a specific type of PDEs, namely parabolic PDEs, and use them for classification, and also to use some of the PDE properties, because we learned back then that if you open a PDE book, there's more than one PDE type in there, all right? So just because we now do deep learning doesn't mean we should forget about that categories. So for parabolic CNNs, it turns out that some things actually work quite nicely, namely carrying information between scales and increasing the number of layers of the network. While for other type of PDEs, namely hyperbolic PDEs, you have other properties of the PDE that you can exploit to increase learning and come up with better algorithms. So that's basically, crash course PDE, a little bit involved here, and it's all based on these papers that we've recently published. So, so just a short introduction. If you haven't heard about a deep CNN, this is how it looks like. So you have some sort of a picture. Then actually you have different layers. In this case, there are 4 layers. The layers cannot have or can have different resolutions. And what is notable is that they have a width. So also called number of channels here. So you take one image, but then here you make it basically 4 images. And in this particular network, they chose to increase the number of channels or the width of the network as you go deeper into the network. Anyway, you process that image, and in the end, you try to classify and do some prediction of what this image shows. That's kind of the rough idea of deep CNNs, and it's exactly the same structure as Eldad pointed out, but the linear operators that are involved here are typically convolutions, and the filters are unknowns. They need to be estimated or learned from the data. And yeah, it has had quite a tremendous success recently. It's like data scientist is now the sexiest job of the 21st century apparently, so there's a lot of hype about this technology for some reasons, but there's a lot of stuff open to be done actually too. Just following what we did before lunch, we don't want to talk about the network like this, so we already established that all we need to describe this phenomenon is we have a yj plus 1, which are the features in the next layer. They are obtained by applying some operator, which now is a convolution to the previous layer, or to the data at the previous layer, and some activation function. Okay, and the linear algebra here would encode which pixels are connected with which other pixels. Okay. Just a brief reminder. So this is again, we study these deep residual neural networks that were record-breaking, I think 2 years ago. And our first contribution was adding this factor of h here, because then you can take a limit and you end up with an ODE system or initial value problem, and see that deep learning is actually the same as the trajectory planning problem, image registration or mass transport. They all kind of follow into the same gist of methods. And in short, we'll probably write the initial value problem like this, where theta are all the network parameters that you need to estimate and that describe the dynamics. Because it is an optimal control problem, so you're not dealing with a fixed set of parameters here. You actually need to optimize them. Okay, so that's the minimization problem we have. We have a loss function that in classification judges how far the predicted label is off from the true label. Then we have some regularizer that uses that, for example, enforces smoothness of the control over time, which is important to ensure stability. And we have the constraint that is given by the forward propagation. Of course, if you have an explicit time-stepping method, you might just drop the constraint and eliminate it and forward propagate and work with that data. Okay, so that's all no news. And here's maybe one picture to summarize why we think of it as a trajectory problem. So this is this example that Eldar showed you before the break, where you have these 5 different classes. And now actually, so the depth of the network, we think about the time dimension of your ODE. And you can follow a feature over time, which gives the trajectory. And you know here that here you can't linearly classify the different classes, but in the final layer you can. And I also visualized here the controls, which kind of control the dynamic and where stuff is flowing. So once you have this perspective, you might want to use this continuous or the dynamic inverse problems view to come up with new analysis and new algorithms. And also, like Eldar encouraged everybody, invent your own architecture. And an architecture, in some sense, is a discretization of this problem. Okay, so let's move to PDEs. That's the main topic for today. So I want to go back to really a 1D signal. So if you have a 1D signal y, and let's say you have like n cells equally spaced, and you want to compute a convolution. So k of theta times y is a convolution where the filter is given by theta. Again, this is what's going to be learned. So that's basically how you write down the convolution, but I can also write down the convolution a little bit more extensively by a linear combination of different stencils. So I can use one stencil which is 1, 2, 1. It's kind of an averaging stencil. I can have one stencil that is minus 1, 0, plus 1 divided by 2h. So there's a central difference. And then here I can have basically a second, or an approximation to the second order difference, right? And of course there's a relationship of 1-to-1 correspondence between these betas and these thetas. It's just a reparametrization. Okay, so once you have this perspective, you might want to go ahead and in the continuous problem say k of theta of t is basically a linear combination of the identity, the first partial derivative and the second partial derivative. Okay? And now again, I mean, you would control this, or you would estimate those parameters beta 1, beta 2, beta 3. And we know from PDE theory that different choices will lead to different characteristics of the PDE, right? And that's really the big insight that we want to bring into deep learning. So from now on, when you see a convolution operator k, always think about it as a differential operator, and always like try to follow through with what kind of PDE will be coming out of this interpretation. I mean, for example, I mean, if beta 3 here was 0 and beta 2 was something and beta 1 would also disappear, then basically you have a convection problem, right? But you can also have a diffusive problem. You can also have an anti-diffusion. I mean, you can build all these pieces, and the choice of theta will influence the stability of your network and all other properties here. Okay, so let's start with the parabolic convolutional neural network. So this is obtained by making the following choice. So if you remember this original ResNet formulation, there was a K2 outside and a K1 inside the nonlinearity. So if we say that K2 is the transpose or minus the transpose of K1, then you end up with the dynamics like this. So you have here a minus K transpose and a K inside. So if you think about K being, for example, a gradient, then this would be kind of a nonlinear diffusion that comes out of this, right? That's why we call it a parabolic network. And here's just one test image to see what the dynamics would look like. So this is just a random filter that I picked, and I compute some like a time series here. And clearly, I mean, you would kind of apply a smoothness filter to that image. It's exactly what we would expect. In this case here, so Albert also mentioned that the stability comes from the Jacobian of your system. So in this case, it's pretty clear, since the nonlinearity always has a positive derivative, at least in the cases that we consider here, that this is a symmetric and negative definite linear system. So, I mean, the eigenvalues should be bounded away from 0 unless there's really a drastic change in the dynamics of the system. So this will be stable, as we know from parabolic PDEs. And yeah, we can, for example, now, since we want to come up with an architecture, we don't actually need to change the architecture. We can just use a forward Euler method and to do the time stepping here. And if h is small enough, also the discrete formulation here will be stable. Okay. And actually, I mean, in image processing, there's a nice paper by Chen and Pock that basically trains those filters to do image denoising, and it turns out to be quite an effective method. So this is not news really to the imaging community, I suppose. But there are other types of networks that we can build. So one network that Elliot also hinted at, which had pretty good stability properties without really losing the information, which would happen in a parabolic network, is the Hamiltonian. So in the Hamiltonian system, you have an auxiliary variable, z, which initially, for example, you set to 0, and then basically the y and the z get updated in alternating fashions if you use a symplectic integrator. And in matrix form, you can also write this, and yeah, basically from this you can derive that the Jacobian would only have imaginary eigenvalues. So this is a type of a hyperbolic system. So let's see how that's doing for that image. So here you see that some part of the signal gets absorbed in the z, and some part stays in the y. But what is maybe notable is that you preserve more of the high frequency, more of the edges. So it kind of seems like an edge filter. And overall, since it's a Hamiltonian system, the overall energy kind of keeps more or less constant, while the parabolic network would decay to 0 eventually. Okay? Yeah, and we use the same Vallée method that Eldad also hinted at. Okay. There's also other options, right? We can choose the PDE, or now it's a PDE actually, to have other characteristics. So in hyperbolic PDEs, there's also like a wave type equation. So if you have a second derivative, I mean, nobody tells you that the y has to only have a first time derivative. And we have basically the same kernel that we had before for the parabolic network. This would be like a wave-like equation. So again, think about k being a gradient operator here. And using leapfrog discretization, you can obtain something that really has a flavor of a wave-like dynamics. So the energy and the information really would not disappear, but you see actually quite a lot of high frequencies coming into that image, right? Okay, so these are all now different options, and what we actually like doing is we like separating them, because in a standard neural network code, you would probably be free to choose any filter, especially when the outer k and the inner k can be different from each other. You basically have no control of what your network is doing. So by construction, we want to commit on a particular type of PDE before we start training. That's kind of one of the philosophies that we have. Okay, so after here, you may wonder, okay, the y basically is an image. So what is an image really? So we think about an image as being a function, right, that assigns each pixel an intensity value. I mean, other people might just think of an image as an array, but typically we prefer the function perspective that we have in the imaging community. So if you do that, then you start thinking about what does actually the classifier in a deep network do. So the last step, after you've propagated all your features, okay, you'll get another image or many copies of your image, but you will multiply your image with a w, which are the classification weights, okay? And this is going to give you the loss. So here's just a simple regression loss function to keep it a little bit light. So y and w we think about as discretizations of some images. So w, since it's multiplied, you compute an inner product between the columns in, or the rows in w and the columns in y. Those are basically images. And if they are images, then we can think about this part in here as really being an integral or discretization of an integral. And if you have that interpretation, you want to add an h square or hx because it's a spatial dimension in a 2D convolution. Because otherwise, I mean, we'll start moving from or from one resolution to another in a second, and you would have to rescale your weights otherwise. And implicitly, that's probably what people are doing. But we want to make this explicit because the scale of the resolution has nothing to do with the values of your w. And also this opens up the interpretation of w when you think about how you want to regularize your weights, because in the end you want the classifier to be such that you generalize very well. So in many applications we think about smoothness, for example, as one nice property of the function w, because this means that noise in the input would not affect the outcome of your classifier so much. And this continuous interpretation really opens up all these floor to, for example, you could also think about a total variation regularizer if you think about piecewise constant classification weights. But that's really, you know, one of these implications of the continuous model. And yeah, similar things you would also find in, for example, log regression or softmax regression, because there's a hypothesis function that is typically built upon the product of w and y. And so in all these cases, we would prefer to add an h square. Cool. So what are some challenges in CNN that are kind of evident if you've worked in the field, but maybe not so transparent for people who are new to this? One is computations. Okay, so training a CNN is computationally costly. Just a toy example, so say you have a width of 16, which is tiny in many applications, and a depth of 20, which means 20 time steps. So then just to do the forward propagation, so to go from your input image to the output image, that's about 5,000 2D convolutions. So this was perceived as being intractable until this happened, and there was a GPU. Okay, this was probably one of the breakthroughs in deep CNNs. But then you start wondering about things like derivative and memories. So if you've solved a dynamic inverse problem before, then you know that the adjoint solve requires your states in principle. I mean, either you need to recompute them or you need to store them. So let's say we want to store them, and for our tiny example here, and say you have like 5K images. Oh, sorry, actually it's supposed to be 50K, I guess, because it's inspired by one example I'm going to show you later. Then easily you can fill up 130 gigabyte of memory, because you need to store all these different copies of your image. Of course, on a GPU you would go to single precision, but the GPU with 65 gig of RAM I still haven't seen, at least not in my lab. So you need to come up with, I mean, either you go to one of these big machines, or you need to come up with some ways of doing like stochastic gradient descent, where you only work on part of the data, or all these different techniques that are out there. But like naive scientific computing approaches would not work here. They need to be tailored to this application. And then a big challenge also is the architecture design. So since training a CNN is costly, you may want to have some theory that says this CNN can generalize better than the other. So if you have some, if you can come up with some theory how to build a CNN that will actually generalize well, I think that will also be quite a good impact here. And then, of course, a CNN should be very difficult to fool, right? So that's the era of adversarial networks. It also relates again to stability. If you add a small perturbation to your image, you would expect the same classification. Otherwise, if you put this technology into a driverless car, something like this can happen. So if you have the right intensity, then you know the car takes this path. But if you like dim the light a little bit, the car would take that path. And that's not a car any of us wants to sit in. And I mean, you have the same in like medical applications. I mean, you really want to kind of control what your CNN is doing, and also there are legal implications that say you need to understand this technology much better. And so these are really hot, I mean, all of these things are hot areas right now where people are actively working on, and where I think our input is it's much more needed also. Okay, so parabolic networks. So let's review the heat equation, because this is the basic, this captures the basic gist of it. So if you have some signal initially, you know, it will just be smoothed out and decay. That's the basic heat equation. So what does that mean for learning? The forward propagation is asymptotically stable. Everything will go to 0 in the end. Okay? So this means that your network is very robust against perturbation of inputs, because everything will go to 0. In the case of an adversarial network, that might be very desirable, because I mean the output will not depend so much on your perturbations. You would have to add a big perturbation to end up in a different place. This also means, though, that the learning problem, so computing those weights, is pretty ill-posed, because in the end you basically solve something like an inverse heat equation. Okay, so that might not be so much good news. On the other hand, there are many numerical methods for parabolic PDEs. For example, multi-scale, multi-level, reduced order modeling, and all these things that can maybe help alleviate some of the computational and memory pressure. So we try to explore that by doing multi-resolution learning. So think about, I give you this image here and I ask you what it is. Okay, it's probably 2 cores. We'll stop when somebody has the answer. So 24 by 24, probably, you know, maybe it's not a car, right? I mean, this we can probably say. Anybody here at 48 by 48? I think I heard the true solution someplace here. Yeah, you can be really, what is it? And one of the above. But the point is that probably at 48 by 48, if you have in your 10 classes, you have cars, airplanes, buildings, or whatever, you know pretty much which one to pick. Okay? So given all the information I gave you on the previous slide about all the computational costs, why would I not train a network on this resolution? And whatever I learn here should tell me something about the fine resolution images. And you can also play the other way around. So for example, if you have a very high resolution input space and you train your network very well, what happens if you take a picture with a smartphone? You want to classify that. You don't want to basically evaluate the high resolution convolution in your network with 5,000 convolutions on your iPhone, because the battery would basically die. So these are things, when you have a continuous model, you can actually go to different resolutions and do learning. Okay, and of course the multi-resolution framework would say, okay, you train on the cores, you get some output, you intelligently prolongate to the next finer mesh, and you start your optimization from there. So the big question is, what do you do with the kernels that you estimate? So say k small h is your fine mesh convolution operator, and k big H is your coarse mesh convolution operator. So then in multigrid, we have a well-known equation that says that if I take a coarse input and I prolongate it, I apply the fine mesh convolution and then restrict the output, I want my coarse mesh operator to do exactly the same. That's coming, basically it's a Galerkin multigrid if you have one more condition, namely that R is equal to a multiple of P transpose. And what does it mean for CNNs? So say I have an image of a 0 on a coarse grid, I have a commutative diagram that first prolongates the image, applies a convolution and restricts it, or I can go directly from here to here without bothering to doing any fine mesh computation. And notably, this kernel is a little different than this kernel. And there is a one-to-one relation between those two scales. So you can take a coarse, so the easy way is to take a fine mesh kernel and make it a coarse mesh kernel, because it's just defined by the system. But you can also go the other way around if you make the assumption that on the fine mesh you kind of keep the kernel size constant. And this requires you to solve, in this case, a 9 by 9 linear system, and you have all the convolutional weights adjusted to the new resolution. You could also ask yourself what happens if I don't do this, which we'll try. So if I just take the coarse mesh kernels that I've learned and apply it to some high resolution image, or the other way around. So that's something we've tried on the MLIS data set. So first we trained on a fine mesh, up to a point where everything was nicely classified. And then we took that kernel to classify coarse images by first interpolating them, but without interpolating them. So really on the coarse data, just pick the kernels that you estimated and go for it. It gives you about 84% accuracy, which is not good for MNIST, because everything you should get is close to 100%. And we were able, with all these tricks of restricting the kernel, getting the age in the classifier right, you get to something like 95%, where you could start and re-optimize your system if you want, or you can just live with that. But basically you get it almost like a 10% accuracy for free just by solving a nonlinear system at each layer. You can also go the other way around, so you can train on coarse and then you classify fine images, and this actually gave a much more impressive disparity between just not caring and just using the old filters you got versus the prolongating. So that's almost like a 30% difference. This image Elliot has talked about, so here we scale. So now we have 2 dimensions actually we can scale network with. So we can scale the image dimension and we can scale the number of layers. And so this is for the number of layers. Playing with image resolution, we also did a more serious example because, as Elliot said, the MNIST example basically always works. So we considered a subset of the ImageNet, which is providing a little bit larger images, like 224 by 224. And again, we used a ResNet, and we tried to first work on the coarse level. So here you see the dotted line is the one to watch out for. The solid line, because this is the accuracy or the classification error of your test data. So that's the one you're not using in the optimization. So you solve using the coarse data, which is cheap, and then you prolongate the kernels and you start on the fine data. And you start in the first epoch. So this is a stochastic optimization method here. So the first pass on your data, you start already much lower in terms of the error. And in the end, actually, you also end up at better minima, even if you let the blue curve, which is just randomly initialized at that resolution, run much longer, almost twice as long, it seems. Okay, so gaining information on the coarse level actually helped in terms of accuracy, and I think also in terms of the runtime. So it was about 20% faster. And this is, for image processing people, this is no news, because this is done in many areas. For example, image registration, it's something we've always been doing. We always first work on a coarse image, because you don't see all the details of the data that distract you and make you end up in a bad local minimum. You would always start very, very coarse and then kind of gradually increase the resolution of your data. And now we have one way also to do that for convolutional neural networks, and especially for parabolic networks, because there the resolution, in the heat equation, the resolution is not really so important after a few time points. Okay, so let's move on to hyperbolic. So hyperbolic equations, this is the standard wave equation, have another interesting property. So they go like this, right? So basically they go back and forth. So this is a nice property if you think about training a network, because I said that one big problem is memory. You always need to store all the states in each hidden layer. In a hyperbolic PDE, you see up here, you can compute the PDE forward or you can compute the PDE backward. So in some sense, in your adjoint, which always goes backward in time, you can just recompute the information that you in the other networks are supposed to save. And a similar property was recently also discovered in the learning community, the deep learning community, namely that there are some architectures that allow you to reorder the computation, so that you go from if you know how to go from yk to yk plus 1, and from xk to xk plus 1, you also know how to go back, just by saving 2 of these layers. So that's called what is a reversible residual neural network, and it came out I think last year. But of course, in fields like full waveform inversion or other hyperbolic PDE constraint optimization, these things have been around for much longer. There are many different ways how to exploit that reversibility. This, recomputing, is only one way to do it, and the hope is to get the memory down much more than the additional computation goes up. Okay? So one question is, so in this deep learning paper here, basically there was no assumptions on f and g. So for any f and g, we can always reverse. So one question is, if something is algebraically reversible, is it also effective in practice? And one thing we might consider is just this very simple case. So say that f is just multiplying z by alpha and g is just scaling the input by beta. Then you get a very simple dynamics. And if you combine two time steps in z, in y, sorry, then, this should be an alpha, and subtract them, this gives you basically an equation like so. So yj plus 1 minus 2 plus alpha beta times yj plus yj minus 1 is equal to 0. So this is something like if you analyze, for example, multi-step methods, that sounds familiar, right? Because there is a solution that is xi to the j, and you can actually compute it. It looks like this if you set all these constants, lump them into A. And now you can ask yourself, okay, what properties of alpha and beta influence the solution to this dynamics? So if you want to be stable, then you want to choose them so that they are less than 1, so equal to 1. Because otherwise, I mean, you see that when you plug that into the quadratic solve. If you don't guarantee that, for example, if they are both positive numbers, this property will in general not hold, then xi will be exponentially growing. So you kind of have an instability that you have built into this system. And that's actually why in the Hamiltonian network we have one positive semi-definite part and one negative semi-definite part, because then this is how you get this number down. And again, so this means that everything that can be, or not everything that you can algebraically reverse engineer, you can also reverse in practice. And think about a parabolic equation. We don't want to backwards compute that because the signal is really lost. Okay. So yeah, for the Hamiltonian we can do this, and we notice it's about like what you would expect, about a 50% more computation, but really large memory savings, especially for very deep architectures. And the Hamiltonian has one nice feature, namely that the eigenvalues are imaginary, so it's basically stable for as many layers as we want to have it if we have smooth time trajectories. So this combines the memory savings and the stability, basically can allow you to have really deep networks. And we had like, I don't know, the thousands of layers or something like that. Yeah. So one question is how does that perform in practice? And we picked one benchmark problem which is called the STL10 data set. It's also natural images. The interesting part is it has only 5,000 training images. So for 10 classes it means about 500 examples per class. And here are some of these images. So it's all over in the animal world, but also there are some airplanes in there to distinguish them from birds and stuff like that. Okay, so we tested quite a few hyperbolic PDEs. So one was the Hamiltonian I've shown you. One is the second order dynamics that I've shown you, so more like the wave equation. So they scored about in the 80% or mid 80% accuracy. This one I didn't cover, but it was also in that range. And here's what other not PDE inspired competitors are doing, and I think it's quite competitive, let's say the least. So we were quite happy with that. We also experimented a little bit with the stability properties, because one intuition that we gained from this is if we ensure that our forward propagation is stable, this should allow us to get away with fewer samples. Because if it's not stable, you need to sample all the data space very well to account for all these unpredictable behavior. And so we tried that with the CFAR10 data set, which consists of 50,000 images, I believe. And this is like 2% of the training data used. This is up to 20%. And the red curve here is the hyperbolic network, and the other one is just the standard ResNet that other people are doing. And you see that the red curve, especially when you have very few training data, dominates the blue curve by quite some percent. So it kind of backs up the claim that stability is important in terms of generalization. We also did that for the STL10 data set, but here, since it's only 5,000 images, I think we only go down to 5% of the data. Okay, so that's some little bit more serious results in terms of experiments. So then some conclusions. Okay, so the main gist, or the main thing to take away from these two talks is that we have a continuous optimal control formulation of deep learning. That's important because this gives us the chance to generate new insights. I mean, it's kind of a nice thing to replace something that kind of people are interested in and that works in many cases, and back it up with new insight that can help the field. But it can also be used to develop new algorithms that maybe scale better, maybe generalize better, or are more efficient to train. Note the relation between a CNN and a PDE, or actually I should say a systems of PDE, because you take one image and in the first layer I told you kind of create all these different copies, and in many cases those images are still coupled together. So you have a coupled system of PDEs that you're dealing with. Yeah, we have some quite promising first results. Well, of course, there's more to be done, but the main thing is that the properties of your CNN depends on the properties of the PDE, or of the type of the PDE that you're working with. So if you kind of don't control or constrain yourself into a particular class of PDEs, you might be in trouble because not every time-stepping method is stable, for example, for a hyperbolic PDE. So if you can, you want to kind of model that into the problem so that you stay within the type of PDE that your solver is meant for. We talked about parabolic CNNs, which relate to anisotropic diffusion, and they are nice in the sense that they allow you to leverage information from different scales, which means image resolution, but also shallow to deep training, which means increasing the number of layers as you go through the problem. And we talked about hyperbolic CNNs, which compare more to full waveform inversion type questions and PD constraint optimization. And they are nice because they preserve high frequencies. Parabolic CNNs would annihilate high frequencies. And depending on which task you are asking, maybe in classification one is better than the other, and in regression it may be the other way around. So just that's the PDE perspective gives you some of these insights. And of course, for hyperbolic CNNs, it's quite a key property is to make those networks reversible, to overcome the burden that your GPU can't hold 160 gigabyte of data for small problems. And yeah, so that's basically the end of my talk. I think I have a pretty selfish ad in the end. So Emory is hiring. Emory is a nice place. So you have different seasons like you have here. Maybe this one is a little more rare and shorter and should be squeezed. But yeah, we have lots of stuff in case you're interested. Jim and I are probably happy to chat with you. Yeah, so thanks for the attention and happy to answer. I think I left plenty of time for questions. So.
Floor is open for questions.
Yeah, thanks for a very nice talk. So you showed a lot of relationships to the PDE world, and so how does you showed a lot of results on the classification of the networks, but there are also for sure also the autoencoders that give you the chance to represent functions. And in the autoencoders, you also have the forward operator and the adjoint operator, which you inherently used. So does that neatly connect to your talk, or is there much more work needed for making that transition?
Well, I can't tell because we haven't looked into this. But for sure, if there's some sort of a dynamic, and I believe there's one dynamic basically going from big to small, and then you go back out. I mean, I would suppose that the properties of one part will affect the properties of the other part. So if you annihilate all your signal until you hit the middle, then probably you have a hard time using that data to generate some output. So maybe you want to think about something that conserves the information, or especially the frequencies. But that's just an uneducated guess. Yeah?
So is it possible to, so you actually choose a very particular network, which is the convolution neural network, and show them their related PDEs. So for an arbitrary neural network, is it possible to generalize it to PDEs in general?
I don't think so.
How would you generalize like a nonlinear PDE, like orthogonal type of thing?
Yeah. I mean, I don't think so, because the PDE structure is a structure of your feature space. So in this case, your features are images, right? In a general neural network, I mean, your features might just be some numbers, like x, y coordinate and the color for the output. So there, I mean, if you have only, say, 2 features, it's difficult to give it a PDE interpretation. So it's a property of the feature space, and then a property of how you propagate your information. For sure, what you do have, and I think Eldad also made that, tried to make that clear, is that the stability properties of your ODE in the previous talk are basically tied to the stability problems of your PDE. So even if your features are not oriented on a grid and have no partial derivative flavor to them, you still care about the same things, that the eigenvalues of your Jacobians are not growing too much into the positive area. So the stability theory is actually quite the same. Yeah?
So this is maybe a naive question, but when you do the PDE formulation of it, does it require then that your convolution kernels have to be local, or can they be non-local?
Wow, that's a pretty interesting idea that ties a little bit to what Eldad mentioned with the implicit time stepping. Because one problem in some sense is if you have pretty local kernels, I mean, they allow you to discretize some PDE operators, but not all of them. Actually, the number of layers you need to propagate information is limited by the kernel size, which may be different in implicit methods if you take the inverse of a convolution operator. But yeah, right now, I mean, that's, CNN is one of these big popular animals, and yeah, people look at very local information. That might not be the best thing to do.
Yeah, you were mentioning at the end about the fact that you typically splitting into multi-channels and then recombining. So that's not obvious that fits in the scheme. I mean, you're calling it a system of PDEs, but if your time evolution involves increasing or decreasing the number of channels, then you have a variable which doesn't exist for the whole time evolution.
Yeah.
It seems really complicated.
Yeah, so actually that's a very good question that I didn't cover very well. Is what you would do in this framework is once you are in one of these layers, you don't change the resolution. So you have an initial value problem, and the number of input features is basically the number of output features. But what people then do is they would say, in a parabolic equation that might make a lot of sense to say, okay, the first 10 time steps I am on a high resolution mesh, but then I have basically one connector that would average that images and create something new, and then you run one more of these blocks. So the overall network will not be a nice dynamical system that takes it from A to B, but it will consist of a few building blocks that you kind of chunk together. So, but within those, you would have the interpretation of a couplet system of PDEs whose parameters you estimate, because that's how the crosstalk between those channels is organized.
Further questions? If not, then I think we should proceed to the next speaker.